Hello, everyone. Thank you for joining us for our webinar. This month, I am so excited. We have Dr. John Wilson and Dr. Charles Newell, who are on the webinar with us. And I've worked with both of these gentlemen for many years, and they really need no introduction as both have made tremendous contributions to our field over time. So they're going to be talking to you today about transitioning from active remedies to M&A. And obviously, these speakers and this topic are of a lot of interest because we have such a large audience today with thousands of people who are attending. In fact, the capacity is larger than the webinar program allows. So if there are any people that wanted to see this that couldn't log on, we are recording the presentation. It'll be available on the resource section of the Microbial Insights website later this week. And everyone that registered for the webinar will receive a link to this recording. So just in case you have problems hearing or you can't get on or you have colleagues that can't get on, that recording will be available for people to see in the future. So as I mentioned, these people need no introduction, but to give you just a little bit of background, Dr. John Wilson has extensive experience in natural attenuation processes and in bioremediation. He is currently the principal scientist with Scissortail Environmental Solutions, and he served as a research microbiologist for the U.S. EPA at the R.S. Kerr Environmental Research Center in Ada, Oklahoma for 35 years. His research for the EPA was primarily on the natural attenuation of BTEX, fuel additives, and chlorinated solvents, as well as in situ bioremediation of the chlorinated compounds. He has over 60 publications. He's co-authored and edited so many reports through the EPA on things from biodegradation to CSIA. And in addition to his research activities, he provides training and technical assistance to the EPA regions and to state agencies. Just a phenomenal person to have. So we're delighted to have you here, John, with us today speaking. And then also we have Dr. Charles Newell, who's the Vice President of GSI Environmental. He has more than 30 years of experience managing environmental engineering projects, has a wealth of knowledge. He's a member of the American Academy of Environmental Engineers, NGWA, an adjunct professor at Rice University. And his professional experience includes site characterization, groundwater modeling, NAPL, source zones, remediation performance, risk assessment, natural attenuation, bioremediation, just a phenomenal amount of experience. So putting these two together really is just an incredible webinar that I hope you can enjoy today. Before we get it started and I turn this webinar over to John and Chuck, I wanted to let everyone know that I have a really exciting announcement. You may have seen this come out earlier this week. Microbial Insights has expanded. We've recently acquired the CSIA and Petroleum Forensics product line from Pace Energy Services. So this gives us a greater ability to meet your customer service needs and to deliver wider capabilities in our CSIA department than we already had, and also to give you added expertise in the forensics of petroleum hydrocarbons. So I'm really excited about this new opportunity to be able to serve you better. If you have questions about this, feel free to reach out to us at info@microbe.com. So as I mentioned earlier, we are recording this webinar today. You're going to get a link that's emailed to you after the webinar. And at the end of the webinar, there's going to be a question and answer period, and we'll go in and ask any of the questions. So if you have things that come up during the presentation, please go ahead and enter those questions into your GoToWebinar control panel under the questions section, and we will answer those at the end of the presentation. If you have questions after the presentation is over, you can also email any additional questions to info@microbe.com. So without any further ado, I'll go ahead and turn it over to you, Dr. Wilson.
We're going to talk about transitioning to monitored natural attenuation. Let me take a few minutes and talk about the reason it's quiet is I'm having trouble with my advancing my slides, which I finally figured out how to do. We're going to talk a little bit about what M&A is from a regulatory point of view. It's actually two different things depending on the end point of the goal. There's M&A used as a risk management tool, and the basic goal is to keep your problem on your side of the fence. And then there's M&A that's used as a remedy just like any other remedy where the goal is to reduce concentrations of contaminants to a cleanup goal. These goals are defined in EPA's guidance on M&A, so this is just provided as a reference for that document. And these are basically the phrases and text that I lifted out of that document, talk about what M&A is in terms of trying to address contamination and achieve an endpoint. In the risk management endpoint, there's talk about stability, and what is meant by that is the attainment of a situation where the plume does not advance into the aquifer and impinge on sentinel wells that are protecting a receptor well or another receptor resource. And so there's wording about where the plume is stable and conditions that would influence that stability over time. There's considerations about uncertainty and understanding the extent of the contamination, its delineation in 2- or 3-dimensional space. There's actually been a little bit of confusion in our practice, our professional practice, about these two goals. As defined by the OSWR directive, stable means confined to a 3-dimensional space, confined within that space delineated by the sentry wells. And so this is the risk management goal. It's distinct and different from the declining trends in concentrations in monitoring wells, which are also a line of evidence for M&A, but that's really more appropriate as M&A as a remedy. We need to keep these two separate goals in mind as we talk about transitioning. Let's talk a little bit about what the public, our customers, the people of the Republic think we're doing with active remedies. I'm going to talk a little bit about, I'm going to talk almost entirely about pump and treat, because that is a primary remedy that we're trying to transition to M&A. So we have a plume that has a possibility of impinging a receptor. We put in a pumped well to intercept that contamination. And so this is sort of the concept people have. The pumped well gathers up the plume over time. And there's some common presumptions to this, that the contamination we're treating is dissolved in the groundwater. And as we pump that contaminated groundwater out, the amount that remains is reduced. And over time, there are fewer and fewer flow paths to the pumped well. The concentrations in that pumped well declines until it's pumped to an endpoint. The real problem, as just about everybody knows on this particular webinar, is there are prenurinating sources for contamination in most sites. And so as the pumped well evolves, contamination evolves through time, what happens is the loose dissolved contamination is in fact captured by the pumped well and removed, but then new contamination is released from the source to sustain the groundwater contamination. So most of the contamination is not dissolved in the moving groundwater at any one time. Most of it is associated with that sequestered source. And so as the groundwater is pumped, it evolves to a point where the amount of contamination is controlled by the release of new contamination. And you get to a point then where the rate of contamination rate of attenuation of contamination really is controlled by the contamination released from the source material. The man that's done the most to help me understand this is Murray Einerson with Haley Aldrich. And so I call this Einerson's observation. When you run a pump and treat system to the point where it approaches this asymptote, the rate of removal of the contaminant in units of mass per time is the rate of release of the contaminant from the source. And so the rate of cleanup of the plume is controlled not by the pumping rate of the well, but by the rate of release from the source. And so I've got my supposition on top of that, that if Murray's right and you get a system to come to equilibrium, you can actually predict or presuppose or forecast the behavior of a pump and treat system if you understand the point rate of attenuation of contamination in the monitoring wells installed in the site before pumping actually started. So I'm going to run through a case study to see if Wilson's supposition of Einerson's observation actually holds together. This is a Superfund enforcement on the large plume of TCE in downtown Albuquerque, New Mexico. New Mexico and most of the Intermountain West is in water famine. Water is precious, and every drop is fought over and litigated. And so this is a pretty high-profile site. This is a depiction of the distribution of contamination at this particular Superfund enforcement action before a pump and treat remedy was put in place. The upper left is plan view. To the right and to the bottom are cross sections showing the distribution of contamination in an aquifer, actually a system of aquifers, stacked aquifers, deposited from alluvia of the Rio Grande River. And so these are the distribution of a number of monitoring wells that was installed at this site before the pumped well initiated a pump and treat remedy. And so you can see that these wells are situated in the hot spot of contamination along a flow path to the pumping well. And so I extracted first order rate constants, K point rate constants, for concentrations in these 6 monitoring wells. And they tended to average somewhere around 0.1, 0.3, 0.6 per year. And there's always 1 or 2 wells where the rate of attenuation is either slow or actually it doesn't attenuate. So I included all the wells that had a reasonable time period, and then took a grand average of the point decay constants. This site also had the advantage that they really had a good job of site characterization, and they went through the process of estimating the total mass of contamination in the plume. So I have a computer model that integrates and collates all the concentrations from all the monitoring points, and then adds it all up. This just shows 2 different time periods where they did that integration of the total mass in the plume. And then the M&A report provided data for 7 years where they estimated the total mass of the plume. That's the data above that blue line. And this basically just a expanded view of the data then that I put a rate constant through. And so the fitted rate constant for the total mass in the plume before they started the pump and treat system is that bottom number, and it's indistinguishable from the first order rate constant of the individual wells. It's really not too surprising, but I offer this to show that they did a pretty good job of understanding the behavior of contaminant concentrations before they turned on the pump and treat system. These are the data for TCE concentrations captured in the pumped well over time. You can see that it's actually fits a pretty good first order rate constant. These are numbers, the rate constant I fit to the time periods when the pump and treat system was actually operating. And then that's the bottom number there. It's actually not statistically different from the rate constants for the monitoring wells before the pump and treat system was put in line. So the rate of attenuation was not different from the rate of attenuation before the pump and treat system. There's really no evidence then that the operation of the pump and treat system affected the time that was required to reach the cleanup goal. So I think we can use this concept or this structure to put together some recommendations. It's like I misspelled recommendations, sorry about that. These are my misspelled recommendations. They're not binding on EPA or any regulatory agency, and My LLC accepts no liability associated with any error that you might make if you implement these recommendations at your own site. So with those caveats in place, let's see what we can do with this sort of idea or concept to decide when it is appropriate to transition to M&A. So I recommend that you run your pump and treat system until you actually get rid of that plume or halo or fringe of TCE or other contamination that's actually in the groundwater. Run it until that rate of capture of the contaminant is in fact the rate of release of the contaminant from the source material. Then operate it for an additional time until you can extract a point rate constant for natural attenuation as controlled by the rate of release. The longer you run it, the more precise that estimate will be. And once you have an estimate that is adequately precise, use that rate constant to project the time by which the concentrations would meet the cleanup goal. And then the final question is the time frame to reach the goal reasonable? And if it is, then you have a basis to transition to M&A. The EPA says reasonable in the basis of other active remedies. The basic default for this that nobody will actually put in writing is somewhere around 20 to 30 years. The reason for that is that most pump and treat remedies are designed such that the design life of the wells and the pumps and the valves and all of that is about 20 to 30 years. So if based on the desires of the local regulators and responsible parties and potential receptors, if that rate constant says it's going to clean up in a reasonable time, then you have a basis to transition. Now, this is for M&A as a remedy. If you're going to transition to M&A as risk management, then again, you operate the system until you suck out all of the stuff that's in the water. Then you go through a traditional M&A risk evaluation process to see if the natural attenuation processes will prevent contamination reaching your receptor. And if the prospects that it will prevent reaching the receptor are acceptable, then you have the basis to transition to M&A. In this particular case, this is a condition in 2005 when they turned on the pump and treat system, and then a condition again in 2012 when they evaluated the pump and treat system and M&A. What you can see is that the pump and treat system basically sucked out the middle of the plume. It did not suck out the source because the source is prenurinating. It's being reestablished by transfer back into the groundwater from sequestered sources. That's the red stuff in the upper left. And the natural attenuation process has prevented the further migration of the leading edge of the plume toward the sentinel wells. In fact, if you look at it closely, you'll see that the leading edge of the plume actually retreated due to the action of the M&A processes. So this is the concept that you want to attain to determine whether you're getting benefit from the investment in an active treatment system and whether it justifies a transition. So at this point, I'm going to transition to my partner in this webinar, Dr. Charles Newell, who will talk about some more sophisticated approaches using monitoring transport and fate software to understand the interactions of these rates and these rate constants.
Great. This is Chuck Newell, and let's just make sure the slides are showing and everybody see problem statements. So what I'm going to do is just sort of give another perspective of this whole issue about a transition and maybe a slight history of our field. It starts out thinking about DNAPL, and in the 1990s we realized something else was down there, making this remediation problem a lot more difficult than we ever thought. And then from this spawned on the bottom left this basically this era of just incredible ingenuity of all these different treatments that we can do to get the DNAPL out. The thought was then these plumes would go away. But then we start looking at this, we realized it's an order of magnitude problem. You need maybe a 99.9% reduction or more. And typically these remediation projects maybe get 90% reduction in concentrations in 99. So what else is happening? On the top right, it was this paradigm shift. There's besides the DNAPL, these contaminants have sort of diffused into these low permeability materials like the silts and the clays. This is called matrix fusion. This serves as this long-term source. And CERTIP and ESTCP put a lot of research on it. That's this report that I was a co-author of, and a lot of implications. But the key implication is we have to start thinking about these sites where active remediation can help us do certain things, but they can't get us all the way there. We have to think about when does we get to the point where these matrix diffusion sources are sort of dominating, where we stop active remediation, we can move on. So I'm going to talk about three different things, a little bit about using a computer model to understand matrix diffusion and maybe help decide when to do this transition, a little bit about mass flux and mass discharge, and then finally a CERTIP project that both John and I are working on that will sort of devote to this idea of transition assessment. Okay, so how does one determine the impact of matrix diffusion? Well, here's just a classic paper from 1995 by Steve Chapman, Beth Parker. This is the key, in some ways, reference about matrix diffusion. It's a site in Connecticut where they had on the left there this source zone, DNAPL. They completely isolated it. And the researchers said, what happened to that plume down there? And they observed that when they went into their coring, that there was 6,600 pounds of TC in this clay silt aquitard below the aquifer itself that had diffused in there over 40 years. That's a lot. So then if you have this matrix fusion source that's sort of under that building in that picture, it's in this aquitard. So what happens? Well, if you do a conventional groundwater model and you say, I'm going to ignore the matrix diffusion, I'm just going to say that source goes away, then this is what something like a conventional transport model would tell you. Oh, that's pretty good. You get rid of that source, the plume cleans up in a couple of years, 2007, everybody's happy. So this is concentration versus time. Note it's a log scale on that y-axis at one of the red dots that's up there in the map, sort of at the far end of this plume. And so this says that if you don't worry about matrix diffusion, we can clean these sites up. But that's not our experience. That's not what's really happened. Now, if you go to 2004, and then I've extended the data on this graph, it still looks like, hey, maybe this prediction by this blue model, no matrix diffusion, is pretty good, and maybe that's what happened. But what actually did happen? Parker and Chapman, they used a research model to look at this matrix diffusion, and they said that plume could last for centuries. And for many years, I would do these talks at the site and say, well, that's where it sort of ended. And so what happened here? Just recently, we worked with Dr. Parker and Steve Chapman, and actually got some data. So what happened to the concentrations? Did they go down, and did the plume clean up in 2007? Or did you see what we call the long tail due to this matrix diffusion? And here's just some new data. I think this is the first time we're actually showing it, that this site, again, these are monitoring wells. It's sort of the far end of this plume. And then if you look over this long period of time, what happened to these concentrations? And these concentrations after about 2003, about the last 15 years, have been really, really stable. And so if you hadn't considered that matrix diffusion, you'd have thought, well, that plume should be cleaning up. But when you think about the matrix diffusion, you can understand why you see this long tail. So how can you better understand this? And one way is using computer models. And there's a new computer model called RemCore MD. That stands for matrix diffusion. You can Google ESTCP, RemCore MD. It's free. You can get it down, written by Dr. Ron Falta at Clemson University. Shala Farhat at GSI helped write the interface for this, or she wrote the interface. And it has these 6 data that you put in there, and part of it's doing the heterogeneity, the matrix diffusion piece, number 4. You also can put in plume biodegradation. Those molecular biological tools are really helpful here. But then if you put this in there, then you can model this. And at this Connecticut site, this is what we saw as the red line. Same graph. That blue line's wrong. That's the no matrix diffusion case. But if you count for that 6,600 pounds of TCE in there, wow, you can see the long tail. And this can give you a better understanding of when doing a transition assessment. If you know this concentration, but better, if you knew the mass flux coming off of that zone, you can understand, well, is natural attenuation going to be robust enough to stop that mass flux coming off that tail? Let's talk a little more about mass flux, and just real briefly, there's 2 versions of the world. There's a concentration perspective and a mass discharge perspective. Let's say I've got 2 sites. Site A, it's a really big source. The groundwater is really fast. The groundwater is so fast, the groundwater wells actually just snap off, okay? And on the right, though, is a tiny source. Groundwater is almost stagnant. But if you think about this from the lens, I'm just a microgram per liter person, you say, well, both of these are the same. But if you count for the size of the source, if you count for the speed of that groundwater, then all of a sudden you can say, site A, I'm going to call that a mega site. I mean, it's really big. There's a lot of mass that's flowing potentially to this receptor. And on the right-hand side, well, what do you call this? Highly technical term, that's a pissant site, okay? There's not much. So this mass discharge perspective gives you this idea of what's a big problem and what's a small problem. Now, how do you develop this? It looks something like this, is you're going to get mass flux. This is the definitions. This is what the ITRC mass flux document tries to stress, is it's the mass per area per time, okay, that's out in there. And so if you integrate that, and that's why I have Sir Isaac Newton here, he will look at this and say, well, if you take that mass flux over that area, then this plume has a mass discharge of, say, 1.5 grams per day. And that's our key metric, is this mass discharge in terms of mass per time. And just a side note, when I was getting a picture for Sir Isaac Newton, I found two amazing things. First, he didn't call calculus. He called it, this is just glorious, the method of fluxion. So that was the first thing I learned about the guy. And second is he had really, really great hair. So our key point here is that doing this mass discharge, you sort of get the mass that goes through this vertical curtain or vertical plane. At any one time, we're talking about grams per day, and you can do a lot with that. Now, one way, and John talked about this is sort of what some of the work that Murray looked at with pump and treat systems, is if you know say of a pumping well, and it's completely captured a plume, well, one of the methods you can get this mass discharge number is just by getting that flow, multiply the concentration in the well, and look at the units, they cancel out, doing grams per liter times liter per day, that will give you this mass discharge in grams per day. So you can get this information from a pump and treat system, and then that can be used to help understand just how strong that remaining source may be if this pump and treat system is only capturing stuff from matrix diffusion. Now, how can you use the mass discharge number? It's sort of the backwards calculation. So if I've got this plume going 2 grams per day that's heading to this extraction well, it's pumping at 600 liters per minute. I just do this division, mass discharge divided by that flow. Hey, the concentration of that well is going to be 2 micrograms per liter. Now, I got to stress, this isn't really the key fundamental way you think about a site. All of our laws are written with, say, concentrations in the aquifer. This is more of a supplemental, more of a supporting thing to do, but can really help you sort of assess risk in this supporting type of a role. The last thing is that, what does it take to impact a well? Let's say we're talking about a contaminant with an MCL of 5 micrograms per liter. We've developed a plume classification system, sort of like a Richter scale. And if you have anywhere between 1,000 and 10,000 grams per day, we call that a MAG 8 plume. The biggest plumes are MAG 10. But this says that if that went into a stream with a mixing zone and a flow about 100 cubic feet per second, man, then that would all get below this MCL. You need a MAG 5 plume, 1 to 10 grams per day, to knock out a municipal well. If that municipal completely captured that plume. And if you have this, well, pissant plume, a MAG 2 plume, that's a 0.01 to 0.001 grams per day, then that you need something that size to knock out a domestic well pumping 150 gallons a day. So that's sort of how you can use this mass flux to gauge impact, not as the primary way, but as this sort of supplementary information about it. So we talked a little bit about modeling, REM-ChlorMD, a little bit about mass flux, Isaac Newton, and mass discharge. And now I'm just going to talk about a CERTA project that John and I are starting, led by Dr. David Adamson at GSI. And basically this DoD research program is really focused on transition assessments. And they funded 1, 2, 3, 4, 5, 6, 7 different projects, and very bottom, well, not just in terms of the numbers they had in there. So I'll talk about this project that we're just starting, transitioning from active remedies to monitored natural attenuation. So here we got this project flow chart, and it's got these different pieces. We're going to have calculators out there to help do some of these plume stability, heterogeneity indicators, going to access to next generation modeling tools that handle matrix diffusion, like REM-ChlorMD. We're going to identifying enhancements to M&A. We're going to be doing some data mining, all this in one web-based tool that you're going to see. So this is what will be sort of out there in about 2 years. Just a couple things with some of the calculators. And one thing we want to do is come up with a matrix diffusion index. And again, this is sort of our idea of indexes and Richter scales and things like this. We like people to be able to put geologic data from boring logs in their site and say, oh, the matrix diffusion index is 1. It's sort of like this uniform sand and lab column. Pretty rare out there in nature. But then you may, if it's a 6, its matrix diffusion is so strong that if you do these injections of amendments, for bioremediation, that may not help you that much because those matrix diffusion sources are so strong. So that's our idea of this matrix diffusion index that we'll develop that people can then say, oh, I'm a 4, I'm a 2, something like that. Next is we're going to do a lot of data mining based on a lot of historical concentration versus time curves. And we're going to give people, they're going to put in data about their site, and we're going to say, you're most like this one site of a 235 site database we have for chlorinated solvent sites. And this is what happened at that site. And these are the error bars that you might see. So we're going to make that on the web, make it easier for people to say, well, who's marched before me? Who tried to do a remediation at a site like mine? What happened? And we'll show you, did it rebound and things of that nature. And finally, here's this next generation computer models. We're going to focus on different ones, but RemChlorMD, which I'm showing here, is one of them. And again, we're looking at use these models to help decide when you make that transition from active to some sort of longer-term monitored natural attenuation. When does active remediation reach this point of limited additional benefit? So we're going to show flowchart and videos, but there's going to be a lot of key breadcrumbs in there to tell people how do you actually use these things, and things like these molecular tools would be one way. How do you put those into the models? And then how do you account for the matrix diffusion at your site? So that's what we have there. Put it all into one big web-based tool so you can go up there and look at it. And then so you go to the different problems and different modules and see what you have in there. So just to wrap up, that pump and treat data, computer tools, they can help you evaluate mass discharge from matrix diffusion sources. And maybe that's the key idea for what if you have that mass discharge, and what the impact would be to receptor wells or to streams or some other receptors that are down there. And then this can be, that mass discharge can be one line of evidence for making the transition from intense active remediation to something that's more passive. And this web tool that's just now starting, and we'll make this a lot easier to do with these different calculators, these tools, and things of that nature. And that's all I have right now for the talk. We go to questions now.
All right. Thank you, Chuck and John. That was an excellent presentation. Let me make sure that let me make sure everybody's unmuted. Okay, so the first question is for you, Dr. Wilson. It says, is there any change in thinking about reasonable restoration timeframes based on the relatively new understanding of back diffusion?
Not to my knowledge, but it's obvious there should be. The important thing to say about that is reasonable time frame is site specific. And it's something that really depends on the mindset and the values that are entertained by that particular region, that particular state about that particular site based on the context of that particular contamination event. The thing about back diffusion really is it's made us realize that pump and treat cannot, in many environments, achieve what we expect it to achieve as a remedy. And so it's a reality check of this is what you want, but this is what you can really have. And it's forced people to think about, well, now what else can we do? But the point of this talk is deciding when, recognizing when, documenting when, explaining when it's time to stop doing something that's not working and transitioning to something that makes more sense. I did not answer the question that was asked. I played a political trick and redefined the question, but I don't apologize for that. The reality of it is that we have a very disparate, widely distributed set of views about this. There's no coalescing on one particular point of view. It is very site specific. That's all I have to say about that.
All right, Chuck, do you have anything that you want to add?
Chuck,
to
maybe I'll just add a little bit to that. Is that that's a difficult problem in the let's see. Just a couple of the things is that the sort of project that I mentioned at the very beginning talked about some of the implications about matrix diffusion. And one of them that it's a management and regulatory problem as well, and that we have these what I call the laws of society that say we got to get everything down to MCLs in a short period of time. The laws of nature say that's going to be really difficult. You're really talking multiple decades or even longer. So there's this conflict in them. And I think the way to get through this is try to say we want to do some sort of active remediation to get the site sort of in a better place, and then let M&A take care of it. So the reasonable time frame is more that first period of just trying to get this place where monitored natural attenuation can take it the rest of the way, because it's going to be a long, long time.
Dora, can I add something to my comment? I guess I'm live. The reasonable time, the reasonable time frame, as originally put forward by EPA, had a supposition that the active remedies were in fact effective, would achieve the goal. And since the active remedies most of the time don't achieve the goal, then that question of reasonable becomes a little less hard to define, or a little less more difficult to define. So there's a basis to reconsider it, but the original question is, has that affected it? And I don't think it has. I don't think the perception has been moved, even though, as Dr. Newell pointed out, what we want and what we can have are two different things. Okay, I'm finished speaking.
No, that makes sense. So Chuck, can you talk a little bit about matrix diffusion from areas down gradient of the source and how strong you think this might be and the impact it has on our models?
Sure. It can be originally the thought was that the matrix diffusion was really where that DNAPL was, because that's where those high concentrations in that source zone are going in there. But then if you look at things like this Connecticut site example, that DNAPL source was completely isolated, and all of that concentrations we're seeing, almost 1,000 micrograms per liter, that's there. That's almost 30 years after they isolated that source. It's still 1,000 micrograms per liter TCE. That's coming from these clays. And so then the realization is that, and some people don't like this sort of depiction of it, is that with these matrix diffusion processes, the plume then becomes the source. That you have this big wide. Now, it's not as strong as a DNAPL source, but it's still very strong. It can keep you above these MCLs for a long period of time. So I think that this matrix diffusion happens in two places, and it certainly happens in these source zones if you clean out the sands with some sort of active remediation. But it's just as pernicious and a difficult problem down gradient, where the stuff that's flowing through those sands, they'll diffuse into the silts and clays that are touching them, and then they'll be this then they will be this long-term source for a long time. So it's definitely a big problem in the plume as well.
John, do you have anything to add to that?
I don't.
Okay. The next question is for you, John. It says on your second to last slide, you talked about acceptable prospects. What do you consider those to be?
Well, again, that's a site-specific situation. In the example site that I talked about in Albuquerque, they built a very solid case for M&A by looking at a number of different processes and trying to associate rate constants with those processes, and then use computer models to project the consequences of those attenuation processes forward in time to predict it. I'm sorry, can you hear me? Okay, I'll start again.
Yeah, you went out for just a minute. Can you repeat that? I'm sorry.
I can hear you, John.
We're talking about we're talking about how to evaluate acceptable prospects. There's a process that has evolved in the United States to evaluate M&A, and it's a combination of computer modeling and in some case microcosm studies and geochemistry of the water and molecular biological tools and some of the new approaches like the work with carbon-14 assays that's developed in Dr. Friedman's lab in Clemson, a variety of different points of view, work using compound-specific isotope analysis. But what you're trying to do is document that there is in fact something out there that's removing the contamination in the aquifer at a rate that would prevent the contamination front from moving forward to impact a receptor. And it works best if you have more than one logical approach to document that process. If you have several different lines of evidence showing that whatever that is, that something is actively acting to attenuate the contamination and prevent the advancement of the contaminant front. Combination of computer modeling, molecular biological tools, CSIA, and probably most important thing, a true and valid understanding of the geological context that supports the flow of groundwater. But you put all that together, and if it all holds together, intersupporting, interconnecting lines of evidence, then you make your case. Then that's the natural attenuation part of monitored natural attenuation. The next step is you watch it for a while and see if your site conceptual model with the computer stuff on top of it, with the lines of evidence on top of that, if it's working, if it's behaving like you think it should behave. And as long as it continues to behave like you think it should behave, you've got monitored natural attenuation. That's all I have to say about that.
All right, perfect. Do you have anything to add to that one, Chuck?
I think that sort of covers it in terms of the, these issues with matrix diffusions and the problems with trying to manage it.
All right. This one is for you, Chuck. Does your model take into account treatment at the source? And what if the source was treated with something like electrical ERH or something similar?
So that's a good question. So we'll just go back to this basically this REMChlor model. And the short answer is yes, that under number 8, if it's still on the screen here, is that it allows you to do this source remediation. So it goes in there and it says you put in the year that the source started, in this case 1952. Then for this Connecticut site, you say in 1991, I'm effectively removing all of the mass from that DNAPL source, 100%, because they isolated the whole zone with this sheet pile, this interlocking sheet pile with these gaskets. And so, yeah, you can go into, and this is a key advantage over some of the other models like BioChlor or BioScreen, which were just natural attenuation. And as Dr. Ron Falta says, no, let's just go in there anytime after that source is put in there, and you can take out all the source or take out 50% of the mass of that source, and then see what happens. In addition, under number 6, you can experiment. Well, what if I do plume biodegradation, and I go ahead and do some sort of injections of lactate or something else, and so for different zones in the plume, you can really turn up those degradation constants and see how that affects it, and also see if those effects are permanent or does the effects of matrix diffusion eventually come out. Now, regarding the different technologies that in the study that one of the studies that I showed in the very first slide is what we call the triangle chart, which looks at 235 different sites, and they included things like thermal treatment, I think, which was part of the question. We looked at chemox, but one of the questions we had in that study, and let me just go to that slide here that we're going to do as part of the CERTA project, is we're going to, if people are interested in doing, some sort of source treatment, we can say, well, what happened when they did it? Is thermal treatment a lot better than the other ones? Our stats from these 235 sites, and we had about 25 thermal sites, I think. We had about 90 biodegradation sites treating the source zone. Thermal was better, but it wasn't statistically better. And so, but people then could use this part of this new CERTA project and sort of get a sense of, oh, well, if I did the thermal, I sort of get this result, and based on these 20 sites that are in this database, 25 sites, if I do biodegradation of the source zone, this is what happened. And so we hope to have this data mining feature in there so people can sort of see what happened before if somebody applied this to a site that's similar to me.
Chuck, you never did get to the triangle site. I think it would be worthwhile to bring that up and show it to the audience. It's in one of your supporting slides.
Oh, is it? Okay.
Yeah.
So it's down here, and it's this chart that, yeah, let's see, I've lost it again.
Yeah, you went past it.
Right here. Okay. So at the bottom of the little panel shows this 235 sites where each dot is a remediation project. And on this one, it just says that the different colors are different types of sites. We have 23 thermals; those are the reds. And then the way this chart works is that the concentration on the x-axis is the concentration in that treatment zone before you actually did the treatment. So this is the starting concentration. Concentration on the y-axis, what it looks like after treatment. Okay, and then the diagonal lines, and both are log scales. Diagonal line are the different orders of magnitude of treatment are in there. And so we learned a lot from this. That the typical in-situ source remediation project can reduce things by about 90%, which is 1 order of magnitude or 1 ohm. That's that first dashed line that's there. And then some can get to 2 orders of magnitude. A couple got to 3. But this sort of talks about what you can expect when you do these source treatments. And so this one does show these different, again, the different technologies behaved in slightly different ways, but they weren't statistically different in there. And maybe a key point is shown on this slide is about 8% of these 235 sites achieved MCLs, and all of the monitoring wells in there, 92% did not. And that's I think this is maybe a key image for us, or data to think about on why we've got to become experts in this transition assessment, and how we can sort of think about managing this. And I think a lot of this is because of matrix diffusion, and how do we manage that?
That's great. All right, I have a question. It's kind of a little longer one for you, John. So it says there was an article that was published by Todd Wiedemeyer where he talked about calculating the rates of attenuation of BTEX compounds for multiple sites. And in the article, he gave averages for the site with minimum, median, and maximum rates of decay. To avoid going through the whole process of calculating this rate for your own site and providing that the hydrocarbon concentrations trends indicate that your plume is decreasing, would it be appropriate to use the minimum values that Wiedemeyer states as a one-size-fits-all? And if not, what do you recommend as the best way to calculate that?
These rate constants are site-specific. The best value of Todd's compilation of rate constants is to actually check and see, one, either does your site make sense compared to the others, or did you possibly make a mistake in your own calculations? There are a number of tools that are available to help you calculate the rate constants. It's easy to do, and that in fact will be one of the support tools in the new transition package that Dr. Newell was talking about. So no, I would not pick a rate constant out of a distribution of other sites. I would calculate my own rate constant. And if you have any questions about how to do that, or you want some support, I provided my email address at the beginning of this. Well, the short answer is find out your own rate constant, understand your own site, do your M&A assessments based on how your site is performing, and use the database as a way of checking to see if your site is making sense, if it's typical, if there's something unusual that deserves further investigation, further characterization.
And this is Chuck. Maybe I'll just add a little bit. Yeah, it basically agree with John. Right now, the way we think about this, that past performance is indicative of future performance when we think about things like the concentration in the plume versus time, and that's basically the standard approach. We do have this research question: is how important is that? Is that really true? And so, as part of the CERTA project, Dave Adamson, John Wilson, and we're going to look at a large body of sites from the GeoTracker world. This is this big California database where every groundwater sample since about 2010 has been put in this database, and we can compile these curves of hundreds or thousands of sites, and then we're going to try to just see how good is this this approach in saying that past performance does give you this leg up on predicting future performance, or does it change, or is it where just taking an average value for all 1,000 sites would be better? So we haven't really started that. We don't have any results on that, but we'll be looking at that and just sort of to sort of give some better foundation for this idea that past performance is indicative of future performance.
Great. Also, Chuck, can you talk a little bit about the availability of the model? And then also another side question is, how do you consider that to work in fractured bedrock?
Oh, two good questions. Let's see if I can find my, here it is. So basically, download it now. Just Google ESTCP and REMChlor MD, and you can get this. It's basically got it's an Excel spreadsheet interface, and then you can go ahead and launch this and use it. And then number 4 is this matrix diffusion piece, and that's new in a lot of these models. Older models don't have this, but it sends you in there, and what on fault it says you have to know 3 things about your site in terms of this matrix diffusion, and I call it sort of the revenge of the geologist, where a lot of chemical engineers like me just sort of thought the subsurface is a sandbox down there. But in this model, that heterogeneity becomes really important, and you need to know sort of the volume fraction of semi-stagnant versus transmissive zones. What's that volume fraction? A typical diffusion depth, or the thickness of these, say, clay layers that's in there, is this other one. And the area, the rough interfacial area. But the model lets you put in, if it's a unconsolidated site, boring logs, and you can put in all your different layers, and it will calculate those 3 terms for you. It will also allow you to model fractured rock. Now, it's a simplified version of fractured rock where it's just one planar. They're assuming a bunch of sort of horizontal planes in there. But then the model's going to say, if you're going to model fractured rock for matrix diffusion, it's going to say what type of media you have. If you got a granite, you don't have much porosity, so it's not going to have a lot of matrix diffusion. You got this limestone, the sandstone, then that starts to be a bigger effect. So it's going to say, what is that typical thickness of that fracture, you know, in centimeters or microns. I think we have, and you can put it in any units you want. And then what is the spacing, basically, of those vertical planes? So the bottom answer is yes. REMChlor MD, Ron Falta wrote it so that it can handle fractured rock. You can understand matrix fusion of fractured rock.
Okay, John, this question's for you. Some states are now mandating cleanup levels that are 1 to 3 orders below MCL of drinking water standards for TCE and vinyl chloride. Do you know of any sites that are being cleaned up to those levels, or do you have advice on what practitioners should do to be able to clean up chlorinated solvents to these ultra low levels?
If I knew how to do that, I would be rich and living in Switzerland. And so I'm not going to give some advice on that. That's I think that's another case of wanting something you can't have. And I'm probably going to make people mad saying that. I think that the issue of trying to clean up below an MCL needs to be something that needs to be evaluated. We live in a world that has risk in it. There is no such thing as a perfectly safe environment or an action that doesn't have more than one consequence. And so, you know, today we're in a world where we are taking extreme precautions to prevent exposure to a new virus. And it's kind of an example of a society working its way through this question of how much risk do we tolerate. But I think setting a cleanup level that's not attainable doesn't serve a government well, because it creates a situation where the whole process of society deciding what it wants and then working together to get to that point just quits working. You're setting a goal that can't be attained. That means the goal won't be attained. That sort of disparages the whole process of trying to attain the goal. I'll get off my soapbox about it. I wish I had an answer to that one.
I think that's a good answer. Do you have anything to add to that one, Chuck?
I think it's a great answer. It's this, again, conflict in some ways, or this tension between the laws of society. They want this to happen, and laws of nature, which says if I have 10 acres of plume where these contaminants have gotten into these low permeability zones, you just can't get those out with our standard technologies very well. And so there is this tension, and I think as an industry, we've got to figure out some way to work around this, where we can transition these sites and let nature take care of those low concentrations, in most scenarios.
Yeah, definitely agree. All right, this one's for you, Chuck. For the upcoming CERTIP project, for your database of remediation sites, is this going to be fixed, or are you looking for more data that will be added over time?
Let's see. It's fixed right now in terms of this leveraging off this older ESTCP project. Informally, though, we're interested in getting more sites, and so in case there ever is an idea to expand it. So definitely send me an email if you got a site with some before concentrations and after concentrations in wells in a treatment zone. I have this informal database that I'm collecting in case we would want to include it in something like this project. So we'd love to see it.
All right, great. All right, we'll take one last question, and then if it's okay with you, both of you, I'd like to send you some questions that we didn't get to during the webinar today. I think there's still some very good ones that weren't addressed, and if you guys answer them, then we'll put them in a PDF document that we can send out to everyone that attended. Would that be okay with both of you?
Yes.
Sure.
Okay, great. All right, so this last one, John, is for you. How do you really distinguish between matrix diffusion and the source area that you have not completely addressed?
Actually, the matrix diffusion acts as a source in the sense that it transfers contamination to the moving groundwater that was not there before. So matrix diffusion basically is another source that has redistributed from the primary point of release. And so the distinction is not a useful distinction to make. Matrix diffusion in that sense is poorly named because it doesn't tell you that what is really being described is the return of contamination back to the moving groundwater. Chuck, you want to add something to that?
It's a little bit. There was a document, 2006, 2010, frequently asked questions about chlorinated solvent sites. It sort of got this cover of that picture on the top right. But this is working with Tom Sale, and you think about these source zones that go through a life cycle. And the beginning one is an early stage site. That's where it does have this DNAPL that's in there. Then a middle stage site is a combination of matrix diffusion and this DNAPL. Then a late stage site, really not much DNAPL left. It's all flowed down gradient, or it's soaked into these clays and silts, or fractured rock into that matrix. And so the way you think about these source zones is there's this transition. And I think a lot of the TCE sites that we have now, many of them are in this late stage where there's not really much DNAPL there at all. And it's mostly this matrix diffusion source that's in there. But that document sort of gives some insight to this idea that these sources, like humans, evolve over time. They're young, then they get middle-aged, then they get older. And the remediation strategy is very different for those three cycles.
Dorothy's time, I would like to add a few more comments to my non-answer. My concept of matrix diffusion basically is the diffusion gradient. Chuck actually showed a picture of one from the work that was done with Beth Parker's site. And I've had a number of sites where we could also map the diffusion gradient by taking very close interval measurements of concentrations in core samples. In that particular environment, you would expect over time that the attenuation of concentrations would follow a first order rate constant. And so if you get weather a site down to the point where further attenuation is first order, then I think you can say that that's very probably matrix diffusion. If it's controlled by dissolution from NAPL, it may or it may not follow first order processes. And one of the powers of the model that Ron Falta developed is that they have a gamma function in the model that describes the particular kinetics of the evolution of the source. And so if you get a value for that gamma function that doesn't make sense based on just simple relaxation and collapse of a diffusion gradient, then you've got another kind of source than just simple back diffusion out of the matrix. I hope that's helpful.
Yeah, I think that's very helpful. All right, well, thank you both so much for sharing your experience with us. I've learned a lot today, and I'm sure everyone else has as well. We do have quite a few questions, so what I'll do is I will put these questions into a document and send over to John and Chuck to go through and answer them. Once we have those answers back, we will PDF that and send out that PDF to everyone that attended the webinar today. Also, this webinar has been recorded, and you will be receiving a link if you registered for the webinar. There's no need to email us about that. That link will already be sent to you. And if you have any questions or need anything further, you can always reach out to us at info@microbe.com, and we will get in touch with both John and Chuck and get answers back to you. So again, thank you both for taking time today, and thank you everyone in the audience for being here. We really appreciate your attendance and taking time out of your busy schedules to be here with us. Thanks, John. Thanks, Chuck.
Welcome.
Mm-hmm.
All right, thank you. Bye-bye.
Bye.